Hello and welcome back, guys, to the second part of our multi-stage events, or our third lesson in probability. Now, I just spent 30 minutes in the last lesson absolutely trashing the tree diagram, talking up about how great the sample space table really is. And yes, that's true, but this lesson is really about the redemption of the tree diagram. Right? For as unwieldy and as large and as sometimes messy as it can get, it is the absolute king of harder multi-stage event questions, even ones that are two stages where you really just want to use that sample space table anyway. For the harder ones, you're going to see when the likelihood of each individual event or branch is different, tree diagrams really are the powerhouse that they are. So let's check it out. For those that are keeping their notes up to date, here it is, the heading and the notes. Pause the video at any point to get your notes in, and let's move on to our first example. Here it is. You drive through a set of traffic lights twice, right? That's typically the case for each day on your way to work or school, then on your way home. You typically see, unless you got like a special different way you go when you go home. But for most people, they see every traffic light. They'll see twice a day. Sad to think, but it's just the way it is. Now, the probability you get stopped at this particular traffic light is 0.6. And so you'd ask yourself, well, is this a good traffic light or a bad traffic light? Unfortunately, it's a bad one. Could be way worse. There's some traffic lights that seem to stop you every single time. But this one's not too bad. 60% of the time, you're getting stopped. 40% of the time, you get to go through. What makes this question a little bit harder than the ones you saw in the last video? Well, if you think about the first example in the last lesson, it was a coin being flipped, right? And a coin is like a 50-50. The heads and the tails, they're equally likely. That's not the case with the traffic light. You're getting stopped 60% of the time, meaning you get to go through without being stopped 40% of the time, right? The events are not equally likely. So if you go back through the notes just on the previous page, read through it carefully, you'll see, hey, when the events are not equally likely, typically you don't have to, but probably it is easiest to pick the tree diagram. And what we do is we multiply along the branches of the arms to get the probabilities. That won't make a whole lot of sense until you actually see a question, and that's what I'm going to show you right now. Okay, so we're going to find, some different probabilities. With multi-stage events by now, these things will be an absolute joke once we have the sample space, I guess. Although even now they'll be a little bit trickier, but still easier. You don't just start trying to guess and that sort of stuff. Let's get our sample space and it'll make the probabilities substantially easier. All right, so we're going to do the tree diagram method here. Because the events were not equally likely, that is, getting stopped and going through is not a 50-50. So I'm going to use tree diagram. Let me show you. All right, so the first time we go through the lights, how many different options are there? Right, let's go to orange. There's two. You either get stopped or you get to go through. You get the green light, right? There's two options. And then again, so that's the first time you see the traffic lights, but we're seeing it a second time that day. So the second time you see the traffic lights, how many different possible options are there? Again, there's two. So from each of the previous branches, there'll be two new branches. You either get stopped or you get to go through without being stopped. You stopped or you get to go. So that leads us with, in total, 4 different possibilities. You get stopped both times, which always seems to be the case, especially on the days where you're in a rush. You get stopped the first time, but, the second time you see the lights, you don't get stopped. You get through in the morning, but you get stopped in the afternoon. Or that fantastic day, you don't stop at all for the traffic light. You get through both times. Okay, so there's 4 different scenarios. And normally, the question would almost be done. You could then just go back and answer the questions. The probability you get stopped both times, There it is. It's 1 out of a total of 4. But it's not quite the case here now because the probability of each of these things is not the same. The probability you getting stopped twice, this situation right here, is actually far more likely than the case where you get to go through both times, right? So it's not a 1 in 4 and 1 in 4, right? We know you're more likely to be stopped than not. So this actually needs to be higher than this, right? So we just can't from this point get our probabilities straight away. And that's why the notes say you need to multiply along the branches to get the probability of each one. These 4 options, these are still the 4 options, right? This is still our sample space, but they're no longer equally likely. Let me show you how to work this out. If you want, you can keep the, the rectangle there. That's cool. That's our sample space, right? No doubts. That is the sample space. Okay, but again, they're not all going to be equal. All right, so let's go back to our tree diagram and let's actually look at the actual branches because these are the numbers we need to multiply. All right, the first time we went to the traffic lights, what was the probability we got stopped? 0.6. Well, what's the probability you get to go through then? It would be the opposite, right? It's going to be 0.4. Sorry, I just quickly need to open the door. Sorry, I've got a 2-year-old that needs to wake up. Okay, then you get on to the next set of branches. Again, this is the second time you go to the traffic lights. The probability you get stopped, it's the same. I know some traffic lights, the likelihood in the morning and the afternoon are different, so you might actually have different values there. But we're not an expert on this particular traffic light. It's just a generic traffic light for a question. Okay, so we actually have listed the probabilities on the arms. The reason we've done that is because now we can actually find the probability of each separate event. And the way we do it is to multiply the probabilities along the branches that led to that point. So the top one, the probability you get stopped both times, well, that was this arm and this arm. So to find that probability, you multiply the probabilities on those arms. 0.6 times 0.6. You have, for this traffic light, a 36% chance of getting stopped both times. I know it was a 60% chance of getting stopped each time, but to be unlucky enough to get stopped both times, not getting through even once, that's going to happen 36% of the time. Now the next one, right, this is this arm and this arm. So to find that probability, multiply those numbers. 0.6 times 0.4, you got 0.24, a 24% chance. The next one, again, multiplying those arms, you get 0.24. Again, these were, getting stopped once, not getting stopped the other time. And the best case scenario, unfortunately, happens to be the most unlikely. Multiplying the arms, you got a 16% chance of not getting stopped at all. Getting lucky on both times, becomes increasingly harder the luckier it is. Anyway, so that's how you find the probabilities. Once you have that, now we can go ahead and answer these questions. What's the probability you get stopped both times? There it is right there. It's 0.36. What was our working out? Right, it was 0.6 times 0.6. What's the probability you get stopped at least once? So on this occasion, for the second one, we actually need to add up all the ones where you're getting stopped at least once. You're genuinely adding them up. And so in this particular case, if you've got a calculator, that's super easy. If not, you're just adding up. Look, it's not too bad. I'll go back to primary school and just sort of, do it as if this was my first lesson ever. You know what? I could have just taken away the 0.16 from 1. That would have been so much easier. Anyway, 0.84. You got an 84% chance of getting stopped at least once. And the probability you don't get stopped, right, that was this bottom one here, 0.16. So these are the harder of the multi-stage event questions. I get it was only a two-stage event, and there was only two options for each one. So our tree diagram actually stayed quite small, but what made this hard was the events weren't equally likely. And when that happens, use your tree diagram, put the probabilities along the individual arms, and then multiply along the arms to get each of the probabilities of the sample space. And then from there, you're pretty good for your probabilities. All right, hopefully that made sense. We're not just, obviously I'll give you more than just one to see, because if this is your first time seeing this, you know, you might be a little bit confused. Pause the video if you need to, rewatch that part if you want. Because I actually want you to have a go at this second example yourself. If you got if you haven't got a book, if you're just watching, you know what, just grab a pen and a scrap bit of paper and just quickly try and see how quickly you can get through and have a crack at this one here. So pause the video. Once you've had a go at the question, unpause the video and I'll go through the answer. All right, so this one here, let's have a look. So the probability of rain on each day of the weekend is 0.2, right? So obviously we're in Australia, the likelihood of rain is always low. In actual fact, 0.2 is quite generous. Even right now, it just doesn't seem to be raining at all. Sorry, I just need a super quick sec. Hey, Angus. Hey, what's good, buddy? Come out. Sorry, Mum's out.
Mom's out.
Yeah. All right, so let's go through our solutions. Sorry about the delay, guys. Okay, so this one here, let's have a look. So, tree diagram. All right, so the first day of the weekend, it's a Saturday. Congratulations. How many different options do we have? Well, within the context of this question, there's two. Either it rains or it's sunny, or a version where it doesn't rain. So that was Saturday, right? There was two options there. And then to complete off your tree diagram for the Sunday, all right, you should have had this. Along the arms, so you should have had, all right, 0.2, 0.2 for all the likelihood that it rains. Again, in the real life, the likelihood of rain between the Saturday and Sunday may have shifted, so it might have been different chances of rain on each day. And again, that would be easy enough if given, the actual probabilities. The question's no harder, right? But I'm trying to do the least amount of writing as possible for myself and for you guys. Anyway, so you should have got a tree diagram looking like this. So the likelihood of getting rain on both days, again, you times those arms together, the numbers along those arms, and you should have got 0.04. In other words, a 4% chance of having rain on both days. Rain and then sunny, multiplying those, that's a 0.8. Okay. In this particular case, you would have ended up with 0.16. The third one down, sunny and then rain, multiplying the arms that lead to that point there, you get the same thing, 0.16. And the most likely case, the situation where both days were sunny, you end up with 0.64. Again, it seems a little low for what we really have at the moment. It's not even summer, but what are we going to do? All right, so this is what you should have got from your tree diagram. Once you have that, you're now set up to find your probabilities. So the first one, what's the probability you have a no rain weekend? Well, that's just the bottom one, 0.64. That was sunny both days. What's the probability it rained both days? Again, that's the top one. You got 0.04, or in other words, a 4% chance of that happening. And this one here, the probability it rained on at least one day, well, again, you're going to add up all the probabilities where it rained at least one day, right? It says the probability it rains at least one day. Just add all up the ones that included at least one day, and you end up with, was that 20, 32, 36. Or, of course, I could have minused, the odd one out from 1, right? Because, again, percentages are out of 100. Probabilities are out of 1. Take it away from 1 and you get the opposite. But anyway, there it is there. So that's that one there. Hopefully you had some success with it. If you made any mistakes, hopefully it now makes sense. If not, you may want to go back over the first example, re-look at it, and then maybe re-attempt that question there. Or alternatively, you could change the situation or the numbers around or whatever it happens to be. It's very simple to recreate your own questions if you want the extra practice. Alternatively, and just send your answers to me. I'm happy to look over and check. But anyway, once you're done with that, let's move on and look at our third example. This is a harder one. That's one of those ones just like the final example in the last lesson. It's one of those ones without replacement. Okay, but again, not equally likely. Here it is, example 3. Let's have a look. A sack contains 5 red, 1 yellow, and 2 blue balls. 2 balls are taken out one at a time. So you got this sack, there's a whole bunch of balls in it. You're going to take out 1 ball and then you're taking out another ball, right? 2 balls taken out one at a time without replacement. And all that means is once you take the first ball out, right, you don't put it back in before you take the second one out. You're keeping that first one out, right? And then you're then taking your second one out. So you end up with 2 balls out.
Mommy out at there.
Very good, Angus. All right, so these are our questions. We're trying to find the probability we get 2 red balls. The probability we get exactly 1 red, and the probability we end up with no reds. So they're asking us to find 3 probabilities. We know not to even worry about the probabilities yet. Once we've got our sample space set up, those probabilities are going to be somewhat of a joke. All right, so let's have a look at our tree diagram. All right, let's start it off. What's the first thing that's happening in this multi-stage event? All right, we're going to be taking a ball out of a sack. All right, what are our different options? Well, we could end up with, when we take the ball out, we could end up with red, yellow, or blue, right? So in this particular case, we have 3 different options: red, yellow, or blue. What's the probability you get the red? Well, in this particular case, there were 5 reds out of a total of 8 balls. The probability you get a yellow is 1 out of 8, and there was 2 blue balls. So it's a 2 and 8. All right, the first ball has been taken out. Let's move on to the second one. So going up to this red ball, right, this first branch, we took out a red ball. How many different options are there for this second ball? Well, there's going to be 3. You could get for your second ball red, yellow, or blue. And, I was going to only put 2 arms for this middle one, but it doesn't make a difference. Let's just say we don't look ahead and we're just like, you know what, the second ball we pull out, you got an option of red, yellow, or blue. Some of you are probably already knowing why I only wanted to include 1 arm on that middle one. But anyway, we'll get to that. 2 arms on that middle one. All right, so let's go through and let's fill out the probabilities for the second one. I really should have used a different color. I'm going to go thinner here to fit it in. All right. Now, what can make these a little bit tricky is we've just taken a ball out, so the probabilities are going to change for this next one. So in this hypothetical scenario where we've taken a red ball out the first time, what's the likelihood of this arm right here? What's the likelihood we get a second red one out? Well, in this case, there would only be 4 red ones left. 4 red ones left. out of a total of now 7 balls, right? A ball has already been taken out of the sack, so there's only 7 left. 4 of them are red. The probability we end up with a yellow, well, that yellow one was still in there out of a total of 7, so that becomes a 1 in 7. And the probability you end up with a blue ball, there was 2 of them left out of 7. Now, the next lot, this is the scenario where the first ball chosen was a yellow, right? So if we got a yellow for our first ball, what's the likelihood we get a red for this arm here? Well, in that case, if we got a yellow on the first, that means we'd have 5 reds left out of a total of 7. Pretty likely scenario there. What's the likelihood we get another yellow? Well, we're down to 0. So it's like 0 out of 7, right? Which is 0. So the whole thing was going to become 0, which is why I was going to leave it out. But you know what? I'll just leave it there. It doesn't matter. And what's the probability of this blue arm? Well, in this case, there'd still be the 2 blue balls there out of a total of 7. All right, and to do the final 3 arms, this is the scenario where the blue was the first one chosen, meaning we have a 5 in 7 for red, a 1 in 7 for yellow, and now only a 1 in 7, because there would only be 1 more blue ball left in the sack. All right, so that's it done, leaving us with our sample spaces, and we know how to find the probabilities. The only real advantage, so I'm still harping on it, of me excluding that middle arm, was there's like 1 less arm to do. It's a little bit less squishy. But anyway, all right, so what's the probability we got 2 red marbles? Again, you just multiply the arms or the branches to get to that end result. In other words, you know, you're multiplying the 5 over 8 times 4 over 7. You times that in your calculator. You press equals. The calculator will simplify it down to 5 over 14. Sorry, I don't have a calculator on me, so I'm going to be delayed here. You're actually going to be quicker than me at this point. The next one along, the likelihood you get the red and then yellow, 5 over 56. The red and then the blue, what is that going to be? 5 over like 28. Yellow and then red, we've already covered that scenario. It's 5 over 56. Yellow and yellow, that's going to become a 0. It's impossible, right? You end up with 1 over 8 times 0 over 7, right? It just becomes 0. It's impossible, which is fine, you know. So it didn't matter if we excluded it straight away, but it also doesn't matter that we included it. It's not going to affect our calculations. Yellow and then blue. So this is going to end up being a, was it 1 over 28? Sorry, I just had a 2-year-old that I think is upset. I'm sorry, I'm distracted. Gotta stay focused. Okay, just super quick. Let's keep going. What is this? 5 over 28. Blue and then yellow would end up being a 1 over 28. And then we have, for the final one, 2 blues. Ends up, well, what does that mean? Again, 1 over 28. Same sort of probabilities are coming up heaps here, to be honest. All right, so there we go there. We finally did it. Took me way too long, way too distracted, but I'm back on with us. Let's finish off this question. Final example of the lesson. All right, so what's the probability we got 2 red marbles? Sorry, 2 red balls. There it is there. It's just this one here. It was, you've got a 5 and 14, you know, times it by 100 if you want to know what that is as a percentage. It's a number. That's the likelihood. What's the probability you get exactly 1 red? So in this case, all you would do is just add up all the ones that had exactly 1 red. So go into your calculator, add those fractions together, press equals, and you get your answer there. I'm going to have to wrap things up because we've got dramas. And the probability you've got no reds. So again, just add up all the ones that do not include any reds at all, right? So you would just take those probabilities, add them all together, and they will give you the answer for this one here. If you have any questions, feel free to let me know through YouTube or on Canvas, and I'll help you the best I can. That is it with our multi-stage events when the likelihoods of different events is uneven. All right, I've got to go. I'll see you later. Bye.